These next three chapters are going to take us through solving differential equations by a method known as the Laplace transform. Now, the idea of a transform, as you can see here from the Wikipedia definition, is to change something into an easier problem to evaluate. And we've done this before. In Calculus 1, we called this substitution. In Calculus 3, we saw how some integrals could be transformed using spherical and cylindrical coordinates into a triple integral that would be easier to evaluate. Now, here's a table from Wikipedia of integral transforms. Now, I'll show you what an integral transform is. The column that you see here labeled with the K stands for the kernel of the integral transform. And I might just point out, we are only going to be discussing this one type of transform. So then, an integral transform is one that looks like this. We are changing the function f of t into the function capital F of s. So we're changing our variables, kind of like we did in Calculus 1 with substitution when we changed it into u's. And the k that you see here is referred to as the kernel of the transform. Now, pointed out on the table that we saw earlier from Wikipedia, that if the kernel here is e to the negative st, then this is what we know as a Laplace transform. And the integral goes, well, we will be using 0 to infinity. So we will have things defined for all positive numbers. Now, the Laplace transform, as you saw again on the table that I showed you earlier, has a cursive looking L as its symbol, and it can take on different looks depending on what textbook you're reading. So let me show you the calculations that we normally would do for the Laplace transform. Here are a few examples. To begin with, we're going to take the function f of t equals 1 and find its Laplace transform. So, according to the definition, we have our kernel, e to the negative st, and the f of t. So we need to literally perform this integral. So to do the integral of e to the negative st with respect to t, we think of the s as being a constant. And to do the integral from 0 to infinity, we do the limit as b goes to infinity of the integral from 0 to b. We did these again back in Calculus 2, I believe it was. So the integral of e to the negative st would be e to the negative st divided by negative s, which we'll put the negative on the e and just leave the s on the bottom. Now we substitute the b and the 0, and then finally evaluate the limit of that. Well, the e to the 0, of course, is just a 1. So this whole term comes out to be just a positive 1 over s. Now this term, as b goes to infinity, we want to investigate what happens there. Notice that as b goes to infinity, if s is positive, we have e to the negative sb, which is the same as 1 over e to the sb. So as long as s is positive, this is going to be getting larger and larger and larger, which means the fraction is going to be getting smaller and smaller and smaller. So it'd be approaching 0. Therefore, this limit comes out to be just a 1 over s. Now, typically what we do is we keep track of these transforms so that when we need them later, like in the next chapter or two, we don't have to keep doing this over and over again. Now we're going to do the integral transform for e to the kt, where the k represents any constant whatsoever. And so here is the definition. We'll do some simplifying and then do the integral of that. We need to substitute the b and the 0 in place of the t. And you can see we've done a little bit of algebra on that. The limit of e to the k minus s times t as over k minus s. This k minus s has absolutely nothing to do with the b, so we can take it out of the limit totally and then substitute the b and the 0. Now, of course, the e to the 0 again is just a 1, so we're still down to, so what happens as b goes to infinity? We'll do a little bit more algebra on this expression, and we notice that as s stays positive, we have k minus s, which again, if that comes out negative, then the limit is going to be 0. So if s is larger than k, then that's going to be, k minus s is going to be negative, and the limit's going to be 0. So the domain of this then is going to be all s is greater than whatever k was. So this is what we end up with. And we will keep track of that in our list. I just wanted to show you the picture of the transforms. Not that it really means anything, but here is the graph of f of t, and here's the graph of the transformed function f of s. In our final example, we're going to find the Laplace transform of f equals t. And so here's our definition. Here's our function that we're transforming. So to do this integral, we need to do an integration by parts. That means we will choose u to be a t and dv to be e to the negative st dt. We'll do the derivative of t, which is 1 dt. We'll do the integral of e to the negative st, which would give us a negative e to the negative st divided by s. And so here's our integral from integration by parts. We need to substitute the b and the 0 and subtract. And again, the key here is in the left-hand side, what does the limit come out to be? Well, you can see all of these that have an e to the negative sb. The limit as b goes to infinity of e to the negative sb, which is a 1 over e to the positive sb. As long as the s is greater than 0, then this is going to come out to be just 0. So again, we'll use the domain of our transformation as just being 0 to infinity, which is fine since we were told in the beginning we just wanted the t's to be greater than 0. And so we come up with just a 1 over s squared. So f of t equals t transforms into 1 over s squared. Now again, all of these are things that we would compile in our list. And so here's f of t equals t, and here's the graph of the transformation. Now, to continue doing this is kind of counterproductive, because the idea that we're headed towards is using Laplace transforms to solve differential equations, which we haven't even gotten to yet. So instead of trying to derive a Laplace transform every time we need to solve a differential equation, we will simply take a look at a table of Laplace transforms, which are available all over the place, and we'll use one in class like this one. Now in this table, you'll notice we have columns for the functions we are transforming using the independent variable t. Now if we have a function involving x's, we just need to think of x's as t's. And we got the transform in the column next to it. So we will use the variable s in the transform. This is just kind of customary. T is the variables we're transforming from, and s is the variables we're transforming to. So here are a couple of properties of Laplace transforms that will be useful as we go throughout doing our Laplace transform. And this simply says that if you've got the sum of two functions, when you do a Laplace transform of that, it's the same as doing the Laplace transform of each one individually and then adding. Same thing would be true for subtracting, of course. And this one simply says the Laplace transform of some constant times a function is the constant times the Laplace transform of the function. You probably recognize these properties from in the beginning when we did limits, and then when we did derivatives, and then when we did integrals. Have the same property for all of them. So here's how the property works. If we want to do the Laplace transform of 1 plus e to the 2t, we'll start by just doing the Laplace transform of the 1, which again we can go look in our table. Then the Laplace transform of e to the 2t. Now both of these we just derived in this video, so you can look at an earlier screen and see what these are. So the Laplace transform of 1 plus e to the 2t would simply be the sum of these two Laplace transforms. We could actually write that as a single quantity by literally adding the two fractions together. We won't worry about that just yet. And so again, we will split this apart and do the Laplace transform of the 3 and the Laplace transform of the 5t. Well, to do the Laplace transform on the 3, we simply think of that as being 3 times 1. And since we've already done the Laplace transform of 1, we can just multiply that by 3. Same thing with the 5t. The Laplace transform on 5t would be 5 times the Laplace transform of t. And we add those two together. Now to finish up our Laplace transforms, we want to take a look at what's called the translation identity, so I can show you what that looks like and how it works. If you need a proof for that, you can see the textbook. However, this is what the translation identity says. And basically what this is saying is that if we know the Laplace transform of a function, such as this, then if we have a factor of e to the alpha t times that, then this would be our transform. Okay, and I'll show you how that works. here we have the function t and what we call the translation, which is e to the 6t. So we simply take the Laplace transform of t, which is 1 over s squared, and we replace the s with s minus x. So there you have it, the translation identity.